Dr. Anthony Raj. He has pursued his bachelor's, master's and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series BSc Physics Honours Mathematical Physics 2 Semester 2 Lecture 16. In this lecture we are going to see Hamilton's principle, modified Hamilton's principle, Legendre transformation, which is an important transformation in the calculus of variation and classical mechanics of physics, Hamiltonian as Legendre transformation of Lagrangian, examples, summary. These are all the concepts we are going to discuss in this lecture. Hamilton's principle. We know Hamilton's principle is about principle of least action. For that, we need to imagine a bead sliding on a curve. That curve, the bead slides in the curve will follow a smallest distance. The time taken to follow a smallest distance is called the Hamilton's principle. So, of all the possible paths along which a dynamical system may move from one point to another in a given time interval, the system actually follows the one that minimizes the time interval of the Lagrangian. This is how the Hamilton's principle is defined. So, alternatively, the same Hamilton's principle can be defined as the Hamilton's principle postulates that motion of a dynamical system from time t1 to t2 is such that the line integral between t1 and t2 L dt is equal to j is an extremum for the correct path of the motion. This is the alternate way of stating Hamilton's principle. Here the Lagrangian is taken into account and j is called the Hamilton's principle function. It is also known as principle of least action. So, Hamilton's principle is nothing but principle of least action. Principle of least action means a bead sliding on a curve follows a smallest path, that is the principle of least action, that is given here of all the different possible paths along which a dynamical system, here the dynamical system is a bead sliding on a curve. That dynamical system may move from one point to another in a given time interval. So, the system actually follows the one that minimizes the time integral of the Lagrangian. This is the definition of Hamiltonian. Here j is called the Hamilton's principle function. It is also known as principle of least action. Next concept in this lecture is modified Hamilton's principle. We learnt that Hamilton's principle is a principle of least action. How can the modified Hamilton's principle can be stated? Here the Hamilton's principle runs as integral between t1 and t2 L dt is equal to 0. This is how the Hamilton's principle runs. Here that L is the function of qi q dot j t, where this qi q dot j are the generalized coordinates and t is a parameter. So, to get the modified Hamilton's principle, let us imagine the Hamilton's principle as integral between t1 t2 L dt is equal to 0, which is nothing but delta of t1 t2, that is small change in this integral, that is mathematically represented as delta of integral between t1 and t2 L qi comma q dot j comma t into dt is equal to 0. Let us keep this as equation 1. But the relation between Lagrangian and Hamiltonian H is given by H of qi comma pi comma t is equal to summation over I pi q dot I minus L of qi q dot I into t. So, this is the relation connecting the Hamiltonian and this Lagrangian. So, the relation between Lagrangian and the Hamiltonian is given by this one. Here this H of q1 qi pi t is the Hamiltonian and L of qi comma q dot I comma t is the Lagrangian. Or this equation can be given in a simplified form as L is equal to summation of pi comma q dot I minus h, where L is the Lagrangian and this h is the Hamiltonian, this pi is the generalized momentum and q dot I is the generalized coordinate. So, from equation 1, the equation 1 we saw is integral delta integral between t1 and t2 L qi comma q dot j comma t dt is equal to 0. This is the equation 1. From this equation we got this one, that is delta of integral between t1 and t2 summation of pi comma q dot I minus h into dt is equal to 0. This is the equation we obtained from equation 1. This relation is referred to as modified Hamilton's principle. So, modified Hamilton's principle is obtained by taking the Hamilton's definition and the general relation connecting Lagrangian, and that too Hamiltonian and the Lagrangian are connected by the equation L is equal to summation of pi comma q dot I minus h. Then we got this small change in the integral t1 t2 summation over pi q dot I minus h into dt is equal to 0. This is the modified Hamilton's principle. So, the next topic in this lecture is Legendre transformation. We know transformation is a mathematical manipulation which changes one coordinate to another coordinate, that is one system of coordinate to another system of coordinate. Legendre transformation. We know transformation is an important quantity or mathematical manipulation in classical mechanics or variational calculus to transform one system of coordinate into another system of coordinate, which is very useful to see a system, a mechanical system in another way. For example, Cartesian coordinate. So, Cartesian coordinate can be transformed into spherical polar coordinate or polar coordinate. Further, that curvilinear coordinates are the basics. All these concepts we learnt in the starting of this course. Here this Legendre transformation is one of a special transformation. It is a mathematical technique for changing the basis from one set of coordinates to another. For example, from Cartesian coordinate system to spherical polar coordinate system or to polar coordinate system. For that, let us imagine a function f which is a function of xi, yi, comma t, be a function of two kinds of variable xi and yi, and t being a parameter. Let us imagine a function f like this. Then the set xi is called the active variables and the set yi is called the derived variables. We know the difference between active variables and derived variables. Active variable displacement, derived variable velocity. So, this is a basic example for active variable and derived variable. So, here in this Legendre transformation, this set xi is the active variable and yi is the derived variable and t is the parameter. So, the differential of this function in the sense differential of this variable with respect to some constant can be written like this. df is the differential of this function f, which is equal to dou f by dou xi into dxi. Here this partial differentiation of f with respect to xi into the full differentiation of x plus dou f by dou yi, here the partial differentiation of f with respect to yi, which is derived variable, into dyi plus dou f by dou t into dt. Here this t is a parameter. So, partial variation of the function f with respect to the parameter t is denoted by this component. So, the differential of this function f is the sum of three components. The first component is partial variation of f with respect to active variable, then the second component is partial variation of f with respect to derived variable, the third component is partial variation of f with respect to the parameter. This is how differential of the function f can be written. Now, this can be expressed in a simplified form as u suffix I into dxi plus v suffix I into dyi plus dou f by dou t into dt. This is how this differential of f can be expressed in a simplified form. Here this ui is taken as dou f by dou xi, then vi is taken as dou f by dou yi. So, this is how this ui and vi are defined. Now, the prime aim of this transformation is to change the set of variable from one coordinate system to another coordinate system. That is the prime aim of this Legendre transformation. To do so, to do that, what we need to do is we need to assume a new set of bases, that is xi is comma yi. xi comma yi are the existing set of variables. We need to transform this existing set of variables to new set of variables ui comma vi. We have incorporated this in the earlier equation itself. So, ui is independent variable. ui is independent variable. There in that equation we saw that xi is an active variable, yi is a derived variable. Here this ui is an independent variable and xi is a dependent variable. xi is an dependent variable. Let us now define the function g. g is equal to summation over I ui into xi minus f. This is how we need to define a new function g, which is very useful in Legendre transformation. Let us keep this as equation 3. Earlier equations are, this is equation 1, then this is equation 2. So, this is equation 3. So, we define a new variable g, which is a function of u and xi. Now, full differentiation of this g, that is variation in g, can be expressed as dg is equal to summation of ui into dxi plus xi into dui minus df. This is how the change in d can be mathematically expressed. Then this change can be further simplified as summation over ui dxi plus xi into dui minus summation ui dxi minus summation vi dyi minus dou f by dou t into dt. So, this is how this dg can be expanded. Dg can be expanded. Keep this as equation 3a. Keep this as equation 3a. From this equation, we get the equation 4. That equation 4 can be written as, which is equal to summation over xi dui minus vi dui minus dou f by dou t into dt. They keep this as equation 4. So, this is the simplified expression for dg. Here it consists dui and vi. So, the relations dou g by dou ui is equal to xi. Keep this as equation 5, and dou g by dou yi, which is equal to minus vi. Keep this as equation 6, and dou g by dou t is equal to minus dou f by dou t. Keep this as equation 7. So, these equations 5, 6 and 7 gives the required Lagrangian Legendre transformation. This equations 5, 6 and 7 gives the required Legendre transformation. So, we can call this dou g by dou ui is equal to xi, and dou g by dou yi is equal to minus vi, and dou g by dou t is equal to minus dou f by dou t as Legendre transformations. Now, using this Legendre transformation, we can get Hamiltonian. We know the Hamilton's principle. From Hamilton's principle also we can obtain the Hamiltonian equation. Then from the principle of least action also we can obtain the Hamiltonian equation. Then from Poisson bracket we can obtain Hamiltonian equation. Here Legendre transformation is also an important way to obtain Hamiltonian equation. Let us see how Hamiltonian equation can be obtained using this Legendre transformation. We know the Lagrangian. Lagrangian L is equal to L of Qi comma Q dot I comma T is the Lagrangian, and this Pi is equal to dou L by dou Q dot. Keep this as equation 1. So, this L is equal to L of q I comma q dot I comma t is the Lagrangian, and p I is equal to dou L by dou q dot is the momentum, canonical momentum, which we got from Lagrangian equation. We know these two definitions. Let us use these two definitions to obtain the Hamiltonian equation from Legendre transformation. We know the Legendre transformation. So, Legendre transformation denoted by H is equal to H of q I comma p I comma t. So, this is the Hamiltonian, then which is equal to summation of p I and q dot I minus L. So, this is the definition of Hamiltonian. Now, by Lagrange equation, by Lagrange's equation, this variation of Lagrangian with respect to the generalized coordinate gives the rate of change of canonical momentum. So, by Lagrange's equation, this dou L by dou q is equal to p dot. Now, go to that variation of Hamiltonian dH. The variation of Hamiltonian dH is equal to summation of q dot I into dpi minus p dot I into dqi minus dou L by dou t into dt. This is how the change in Hamiltonian or variation in Hamiltonian can be mathematically given in terms of the generalized coordinate q, Lagrangian L and canonical momentum p. Now, this dou h by dou p j is equal to q dot j, and dou h by dou q j is equal to minus p dot j, So, then dou h by dou t is equal to minus dou L by dou t. So, these are all the Hamiltonian's equation. These Hamiltonian equations are obtained from the Legendre transformation. Legendre transformation, we know, is an important concept in the calculus of variation to transform one entity to other coordinate system, that is Legendre transformation. That transformation is used here to obtain the Hamiltonian equation. The next topic we are going to discuss is the inverse Legendre transformation. This inverse Legendre transformation is used to show that Legendre transform maintains all of the information in the original function. Here what this statement says is, let us imagine a function y is equal to f of x. If that y is equal to f of x is transformed to some other coordinate system, the originality of the function will remain as it is. That is what this inverse Legendre transformation says. Now, we will see how this inverse Legendre transformation maintains all information in its original form. So, we will see that. To do this, compute the derivative g of p. So, g of p, derivative of this g of p is a function where g is a function of p. Derivative of this g of p is given by dg of p over dp. This is the derivative of g of p, which is equal to d by dp of p x dot minus f of x dot. So, this is how this dg of p is mathematically expressed. This can be further expanded as P into dx dot of P over dP plus x dot minus df of x dot by dx into dx dot P over dP. So, this is how this can be expanded. This can be expanded. Now, further expansion of this gives P into dx dot of P over dP plus x dot minus P into dx dot of P over dP. Here this df of x dot over dx is taken as P. So, here df of x dot over dx exists. So, this is taken as P. So, this component is reduced to the form P into dx dot of P over dP. In this derivation, we are going to see the inverse Legendre transformation, and we know that we learnt that the inverse Legendre transformation is going to maintain its originality, or it is going to maintain the originality of the function we are going to see in this derivation, which is equal to x dot. So, we got that dg of P over dP is equal to x dot. Then compute h of y, which is identically equal to Lagrangian of this g of P, identically equal to Lagrangian of this g of P. So, Lagrangian of this g of P is equal to y p dot minus g of p dot. This is the Lagrangian of g of P, where we used the expression dg of p dot over dP is equal to y. So, substituting for this g of p dot from this expression, we get dg of p dot over dP is equal to x dot, which is equal to y. So, from this we got this originality of the function is retained. We got that g of p, that g of p is derived, that g of p is derived. Then we got y, which is the originality of the function, and inverse Legendre transformation retains the original function. That is the concept we learned from this inverse Legendre transformation. So, from this lecture we learned the Hamilton's principle. Hamilton's principle explains the principle of least action, and explains the least path followed by a body in a curved motion. Then Legendre transformation, an important transformation which transforms the coordinates into other coordinates, into other variables. Then Hamilton's equation, Hamiltonian equation are obtained from Legendre transformation. Then inverse Legendre transformation, which keeps the originality of the function. These are all the concepts we learnt from this lecture. After listening to this lecture, we can answer the following questions. Define Hamilton's principle, then what is known as Legendre transformation, then give Hamilton's equation from Legendre transformation. These questions can be answered after listening to this lecture. Thank you.
Right.